I don't think I don't like it's not I think like all right, let's get started with today's lecture. I'm going to continue with what we talked about in PowerPoint, but do it in R, so you're familiar with how to do these types of things. The first thing that I want to talk about, though, is logistics. Next week is Thanksgiving break, and so there's no classes during that time. There's not going to be any assignments due. But what I am expecting to do is to grade your project first drafts during Thanksgiving break so that you have some time to make those changes. Remember that first draft is due on Friday. I also changed the syllabus a little bit so that instead of having a quiz on Friday, we're going to have a quiz on Wednesday so that more students can actually take the quiz. And we're not going to have discussion on Thursday or lecture on Friday. So you get an extra long break. I also don't want to be introducing a ton of new concepts that you'll probably forget about during break. So just to make it easier for everyone, we're taking those days off. All right. Before I start, are there any questions about the class, either logistics or any material? Question here. Yeah, so the quiz is going to cover a little bit about Garch models and a little bit about binary dependent variables, or the categorical dependent variables. So those two concepts, really. Any other questions? All right. Then the first thing we're going to do today is import the health expenditures data. You did some of this during discussion, but I want to go over it so that we all understand what's going on. So this first line clearly just reads in the CSV file. This next line makes an adjustment to the race column. So there's already a race column, but in the book, they combine other race with the white race. And so that's what I do here. I set up an if-else statement where the first argument is the logical condition to check. And so what I'm trying to do here is say, if the race is other, then set it to white. Otherwise, don't change it. Set it as the race. And then replace the race column with those changes. That just makes it so that it matches the textbook. There's not a particular reason why we need to do that. The file contains medical information, and we're looking at whether or not someone gets hospitalized. That indicator is not present in the data, but that's the nice thing about data exploration. We can create our own variables based off of the data that we're given. And so if you are more concerned about whether or not someone gets hospitalized, you don't care how much the cost is. And so we're converting a continuous variable into an indicator variable. So if there is positive expenditure for an inpatient visit, that means someone went to the hospital and they stayed there overnight. and that there's a positive expenditure, so it's not so that there's actually a visit. So I once again set up a if else statement, if then else statement, saying if there is positive inpatient expenditure, then the indicator is going to be 1, meaning they are hospitalized, and 0 otherwise. And then I replicate the table that's given in the textbook using the table function. Table function simply just creates a table of the counts for each one of these pieces in the range. So there's only 2 options. Either there is a hospitalization or there is not a hospitalization. And then on the other axis, we have gender. So here 0 means male and 1 means female. Based off this table, it's not labeled, so you can't 100% tell right off the bat what each axis is, but the top axis is the gender, and this vertical axis is the hospitalization. It should sort of make sense because there's about equal amount of men and women, but there's a lot more people that are not hospitalized than are hospitalized. So, for example, this value here means that there were 941 females that were not hospitalized. So this is the difference between what we did with linear regression. In linear regression, we had a continuous dependent variable. Here we have a discrete random variable. And to be more specific, we have a binary dependent variable, either 0 or 1. So we can't use the same techniques because, for example, if we're trying to calculate a probability, it has to be in between 0 and 1. To create a logistic regression in R, we need to use a generalized linear model. The generalized part of the linear model tells us how we're going to relate our linear model to our y variable. So the generalized part is saying that we still have a linear function, beta 0 plus beta 1 x1 plus beta 2 x2, and that gives us a value, but that does not match our y's. We apply a function to that linear combination to get whatever our y value is supposed to be. So in this case, our y values are 0s or 1. And so we use a general linear model to calculate the probabilities of getting 0 and 1. One thing that I want to make clear about regressions is that regressions are really about giving you probability distributions. In linear regression, our probability distribution was a normal variable where our average was the expected value or the fitted value, and then our variance was given by S. Here, our probability distribution is discrete. So we're going to have certain probabilities of different outcomes. And in this case, it's going to be a Bernoulli outcome because we have that there's either a success or a failure. And there's only one trial for each observation. Okay, so to use the GLM model, we have to explain what the relationship of the residuals will look like. And that is done through the family argument. So this family argument here tells us what our residuals look like. And in this case, our residuals, because it's 0 and 1, that's a binomial. If you don't include anything about the link function, it will assume as a default a logit link function. And we'll see later on how to change that. So the first thing, this first piece of code brings up the help menu for GLM. which I have over here. Oops. And you can see that has some similar ideas to the linear models. You need a formula, you need to include some data. The additional thing that we're going to be working with is the family. And so, the family can be from a bunch of different options. I'm trying to find where it says. If you click on the family part, it'll tell you what all the different options for families are. I want to bring this up to sort of give a hint of where we're going in the future. So we have the binomial family, meaning that our observations are binary 0 or 1. And we have a link that equals the logit. So the different links we talked about were the logit and the probit. There are some other links, but these are the common types of links. The length function tells you how to convert your linear combination into a probability. So use the logit function or the probit function. If you look one below, we have the Gaussian. A Gaussian is a normal random variable. So if your errors are normally distributed, then that means that you just have a regular linear regression. And in that case, the length function is called the identity because you just use pi of z equals z. You just use the linear combination as the prediction for the y value. So you could do everything we've done with linear models using a general linear model if you consider a Gaussian family of residuals with an identity length function. So we've talked about two different types of y variables: continuous y variables, where you use a Gaussian type of error, a normal error, and the length function is identity, meaning that the linear combination is what the y values are. There is another type that we talked about, that we've been talking about recently, is the categorical type, where you have different categories and you're trying to decide between success and failure. There is a third type of dependent variable that we'll talk about after break, which deals with a Poisson family. This is an example when you try to ask a question like, how many customers are going to enter the store today? That, in that case, your y variable is a whole number, 0, 1, 2, 3, and theoretically, it has an infinite limit. You don't want to stop counting at any point. You might have something like, I want to see how many people enter Walmart during a year, and you might have millions of people or thousands of people that go through in a particular store throughout a year. And so that's a little bit different than what we discussed, because you see values like 1, 2, 3, 4, 5. They are ordered, but they're not separate categories, because having 4 people is really different than having is really twice as many as having 2 people. And so that's another type of regression we'll see later on that requires the Poisson distribution. But anyways, back to our file. That's a little bit about the generalized linear model function. What I have here is an example of a logit regression. We use the GLM function, and we define a function, or I should say a formula. We're going to regress hospitalization on all these explanatory variables. The data is coming from health expenditures, and our family is binomial. So this is the output for that model. It tells us the coefficients for all these terms, and it tells us degrees of freedom, null deviance, residual deviance, all that. So the null deviance is the like the standard deviation of the y's. The residual deviance is the residual of, the deviance, the standard deviation of our residuals. They don't use the term standard deviation because our residuals look a little bit different in this case. But the general thing to interpret is that if there's a positive coefficient, that increases the probability. If there's a negative coefficient, that decreases the probability. Okay. We talked about why some of these coefficients are different between this model and the model that's given in the PowerPoint and the book. And one of the things that we discussed was the fact that you can relabel the levels of these explanatory variables. For example, if you consider the race variable, you have Native American, you have Black, you have white, and Asian. In this regression, Asian is the baseline, but in the book, they use white as the baseline. In general, there does not need to be a specific variable that has to be the baseline, but there are some things that are done in practice. One idea is to use the group that has the most observations. And in this data set, there are more white people than there are of any other race. And so they use the biggest population as a baseline. That's one way to do it. Another way to do it is to figure out which race is going to give you the largest or smallest coefficient, and then use that as the baseline so that all the coefficients are either positive or negative for that explanatory variable. So we could have made it so that all these terms had the same sign. Race Native, race Black, race white, all that stuff. But that just explains why it might look a little bit different. They are the same regression, though. Meaning that they give you the same fitted values. And just the way they get to those fitted values is slightly different. All right, that's the logic model. We can create a probit model by adding some information. The only difference between a probit and a logit model is the link function that's used. The link function is how you relate the linear combination to the probabilities. So in order to create a probit regression, we add, on top of the family being a binomial, that means that the errors are 0, 1, or outcomes are 0, 1. We include the link argument to note that the link function is the probit function. And when you do that, you'll get a slightly different set of coefficients, but it should follow mostly the same sort of interpretation. So I would be surprised if there was a coefficient in the logit model that was positive but was negative in the probit model, right? They should also follow approximately the same sort of scaling meaning that if you have one variable that's approximately twice the other, it should stay that way when you switch models. So let's compare something like income. We have, it's kind of hard to see. Okay, we have low income, medium income, poor, and another poor category. Let's compare that to the coefficients in this model. So on the left, I have the probit model. On the right, I have the logit model. And what I wanted to look at was the income poor category. So here, it's about 0.92, while the low income is about 0.5. That's for the logit model. Here, we have poor income is 0.4 and low income is about 0.2. So they're both about halved when you go from the logit model to the probit model. That's the relationship that I'm really talking about. It turns out that a lot of the coefficients will be approximately halved just by the way that the function is described. Okay, it's not exactly half, but it just has to do with the formula for the probability distribution function. So all these sort of interpretation that you would do for a logit model is pretty similar for a probit model. The main difference, though, is this sort of interpretation that we have. We saw with logistic regressions that the linear combination that we find is a log odds, while for a probit model, it's not, it doesn't have that interpretation. Instead of it being a log odds, it's a value in the normal distribution. Okay, so outputting just the GLM gets us the information on the coefficients. If you do a summary, then similar to simple linear regression, you'll have a bunch of coefficients, there's standard errors, and some p-values. So these values, this isn't much different than what we've seen before. The z-values are actually, you can think about these as the t-ratios, how many standard deviations away from zero you are. And so for a lot of these, they are not very far away from zero. But we have to remember that a lot of these variables are discrete variables or categorical variables. So you should look at the combined impact of all the variables before deciding to get rid of one of them. So what I mean is that, for example, here, these variables stand for the physical status of the individual, whether they are physically healthy or not. And we can see that if you are in poor physical state, that is a big indicator of whether or not you're going to go to the hospital. And so because this variable is important, is very important in this regression, we probably are going to include all the other variables that are associated with it. However, we could, looking at this, make an indicator, once again, decide between whether someone has poor physical health or doesn't have poor physical health. You want to do that. But that's not 100% necessary. This gives us a little bit more granularity. But it also leads to some weird interpretations. For example, the difference between being in very good physical health, 0.09, in good physical health, 0.18, would lead you to believe that being in better physical health reduces the coefficient, right? Being in poor health is 0.9. Being in very good health is 0.09. However, being in fair health, which to me is less than good health, but better than poor health, is actually the minimum coefficient here. So there's a little bit of investigation you should do when you're looking at these coefficients to see if they make sense. This is probably a statistical artifact. What I would want to know is how many individuals are in this category. It seems that most individuals are in the very good or in the good category because they have a lower standard error. But that could just mean that they're less variable. Who knows? Anyways, that's a little bit of interpretation for these coefficients. The next idea that I want to talk about is really going in depth with the probit and logit models. So let's really dive deep into what the logit and probit model are. The logit model has a PDF, a probability distribution function, or density function, of f of y equals e to the y divided by 1 plus e to the y squared. So you've all taken some sort of probability class. You understand what this means. The probability that y equals 0 is 0, but if you want to find the probability that y is in between 0 and 1, you could integrate this function from 0 to 1 to find the probability. This leads us to the idea of the cumulative distribution function, which is the integral of the PDF from negative infinity up to y, which is equal to 1 divided by 1 plus e to the y. Now, there are a couple things about probability distribution functions that you should know. Wait, this doesn't look right. I think this is supposed to be a negative y here. Because if you plug in negative infinity into here, you should get 0. And if you plug in infinity into here, you should get 1. This is true for all CDFs. Because if you're looking at the probability that your value is less than negative infinity, that should be 0. If you're looking for the probability that your value is less than infinity, that should be equal to 1. All right. So, what exactly is meant by a logistic regression? Well, it is a regression that models the probability of an event taking place by having the log odds for the event be a linear combination of the explanatory variables. That statement has a lot to unpack in there. But the important part is that the function that converts the log odds to a probability is the logistic function. So the logistic function is nice because it has this theoretical interpretation. If you use a logistic regression, then the linear combination that you're calculating is what is called a log odds. So it's the logarithm of the probability that y equals 1 divided by the probability that y equals 0. That can vary from negative infinity to positive infinity. So the logistic in logistic regression refers to the function that relates the linear combination to the probability. In other words, we use the logistic function as the pi function in the relationship. The probability that y equals 1 equals 1 over 1 plus the exponential of negative xb. So if this linear combination is very large, that means that our probability is very high. While if our XB is very small or very large and negative, that means our probability is going to be very low. And another thing to note is that these probabilities are bounded between 0 and 1 because of this function. So that's a nice interpretation. The probit model has a probability distribution function of the standard normal distribution. So its probability density function is 1 over the square root of 2 pi e raised to negative y squared over 2. That's for a standard normal. The important thing here is that we have an e raised to negative y squared over 2. Compare that to the logit function, which had e to the y divided by 1 plus e to the y squared. And the main thing being that they both involve exponentials. The nice thing about the logit distribution is that you can actually integrate this and get a nice value like this. While for the normal distribution, that is not a nice function. Instead, the cumulative distribution function for the normal distribution is noted either as n of y or phi of y. And it is the integral from negative infinity to y of the PDF. So this represents the probability of being up to a point y in a standard normal distribution. I plotted the PDFs for the logit and probit models here. I'll go through the code and then show what the plot looks like. So I created a sequence of x values from -5 to 5. I inputted a value for pi. And here we have the formula for the distribution of the logit. There's some pi's and square roots 3 in here. That has to do with the mean and standard deviation of the logit. And this is just done to sort of map out the PDF, right? We're getting different percentiles, and so we're plugging it into here to get like the 1 percentile, 2 percentile, 3 percentile, and so on. And then we use the d-norm function to get the density of the normal function. I then plot the logit, x against the logit, colored red. I then include the probit model in blue. And this is what we get. In red, we have the logit case. In blue, we have the probit case. And you can see they look very similar. There's a little bit of difference in the center, where the logit case has a higher peak. But the logit also decays pretty quickly. And so they look very similar in most of the range. And so that's why when you use them, you're going to get pretty similar interpretations of the coefficients. The coefficients are going to be a little bit different because of this difference in the area, but the interpretations will be pretty similar. All right. I then decided to simulate a logistic regression so that we get a better idea of what's going on here. So to simulate a logistic regression, the key point is that I need to use the logistic function to convert the linear combination into probabilities. So I want to go step by step here. First thing you do is set the seed. Then I set the range of x's, and I do a number of repeats. So what this means is that there's going to be 100 observations where x equals 1, 100 observations where x equals 2, up to 100 observations where x equals 100. That's what this value is. So this is just going to be 1, 2, 3 up to 99, 100, and then it's going to repeat again. 1, 2, 3 up to 100. I then perform a linear combination, and this linear combination tells me the log odds. I then use the log odds to create a probability, constructing probabilities using the logit function. So these probabilities tell me the probability that this observation is going to be 0 or the probability that's going to be 1. I then use a random uniform distribution between 0 and 1 to determine whether that probability is large enough. That is in our y's. If this random uniform is larger than our probability, then we're going to say it does not succeed. But if it's less than our probability, then we say it does succeed. And that's determined by 0 and 1. I then run a general linear model predicting y's on x's using a binomial family. And then I get a summary. So what I want to show is I did this so that the output is the same thing as my linear combination here. It should look like 2x minus 50, which in fact is what is done here. So because of the randomness in the model, these values aren't exact, but we can see that they are within a standard error of the correct values, which is nice. Okay, we have an x of 2.1 and a standard error of about 0.2. And we also have an intercept of negative 52 with a standard error of about 4. So they're both about half of a standard error away from their true values. So you can look at this example and see how the logistic regression really works. Okay, the first question I have in our file, change the code. Whoops, there's supposed to be code. And then use the p-norm function to find the probability from a normal distribution. So I'm going to change this code above to make it work for a logistic distribution. So the first thing is I want to change it to a probit distribution. In order to do that, I need to use the p-norm function. The p-norm function gives us a draw from a normal distribution, which is the link function here. So we need r times n draws from a standard normal distribution, a mean of 0 and standard deviation of 1. Okay, and this is no longer a log model, so I'm going to call it a probit model. I need to include information about the link. And then I want to find a summary for this probit model. So let's run that. I did something wrong. Let me see what I did here. Oh, whoops, not RN, LC. Sorry. Yeah, so I was trying to find the probability associated with this linear combination. And that once again gets me something very similar. We have an x value of about 2, an intercept of about negative 50. Just to demonstrate that this does work, let's use a negative 3 here, and let's make this 80 here. Rerun it, and oh, well, actually, I want to make this plus 80. Oops. Oh, whoops. I'm going to do this. And we'll see that if you do change these parameters, it does flow through into the GLM formula. Okay. Question 2. How can we change the algorithm to reduce the standard error? So a standard error has to do with how spread out our predictions are. So we can increase the range of x values, which is r. We can increase the number of observations with n. And a more coding-centric change is that we could change the code so that p% of observations are successes instead of having each observation, instead of giving each observation a p% chance for success. That last point, I kind of want to explain a little bit. In the simulation that I did, I gave every observation a p% chance to succeed. That was from the random uniform distribution. However, this injects some randomness into our simulation, because let's say that I calculate that 50% of observations should be successes. Well, if I actually run a simulation, it's rare to have exactly 50% of them be successes. Usually you'll have like 52%, 48%, something like that. I could have changed it so that exactly p% of the observations are successes instead of giving them a p% chance. This makes it so that if you change the seed, you might get a different outcome. For example, okay, if I run up here, I have negative 51.879. Let's say I just change this. I now have a completely different, well, they're still pretty close, but it is a little bit off because I changed the seed value. That has to do with the randomness of the random uniform. Just so that everyone knows, this is not run if, this is random uniform. I always misread this function as a run if function. Then I'm expecting an if then statement. No, this stands for random uniform. Okay. So those are some ways that we could improve the model, reduce the standard error to be more accurate about our predictions, or more precise. The next thing that I want to talk about are multi-category regressions. So the first thing that we need for this is the nnet package. So you should run that package. I already have it installed. And this will allow us to run the multinomial function. Before we do that, I want to make sure that we all understand what's going on here. What is the difference between a nominal set and an ordinal set? A nominal set is in name only, meaning that the categories do not have an order. An ordinal set has a natural ordering. Compare the set gold, silver, bronze to the set. Actually, compare. Let's call this north, south, east, west to gold, silver, bronze. In the first set, there's not really an ordering that is significant. It is not like north is better than south or that east is better than west. However, in the second set, gold is better than silver and silver is better than bronze. All right, let's plot the iris data set. Which variable would you use to predict species? Well, let's plot iris and see what it looks like. So what I want you to look at is the last row or the last column. The last row here, last column, these are all related to the species variable. Okay? So looking at sepal length, I don't think sepal length is the best option here because there is a lot of overlap between the different species. To get the best model, we should use where there's the least amount of overlap, which I think is either petal length or petal width. The sepal length and width have a lot of overlap, so the probabilities are going to be close to 1/3 because there's 3 categories. While here, if you're in this range, you're definitely in this species, which is Setosa. While if you're here, you might be a different species. Here it's unclear, but if you're in the upper range, then you're definitely whatever the species this is. So I'm going to use petal length. Petal length can use to distinguish between species. Okay? So in the sense, we're finding a model that tells us, okay, if you don't know what species this flower is, measure its petal length, and then we can give you a probability that's a Setosa, versicolor, virginica, anything like that. So let's use the multinomial function to run a regression on the species variable. The first thing I do is use the library command to tell R that we're using this package. I then ask R about this function and run a model. The output looks like this. You don't have to worry about it so much, but what it's telling you is that these are like likelihood, not likelihoods, but these are like standard deviations that occur. And what it does is that it doesn't really know what coefficients to give each of the values. So it just tries a bunch of different coefficients to improve accuracy, reduce standard deviation, all that. And after some point, it'll stop. You'll see that after about 50 iterations, it gets to approximately the value that we're going to use. But it keeps on trying to improve, reduce this value a little bit. Anyways, what we really care about is the summary, which tells us what the coefficients are. So we're trying to find a species based off of petal length. The formula that we get for versicolor and virginica. So in this case, we're using Setosa as the baseline. It's not included in the output. What these things mean, because we're using a logistic regression, this means that the log odds are given by this linear combination. -23 plus 9.2 times the petal length gives us our log odds. Okay? Remember, our linear combination can be anything from negative infinity to positive infinity. If it's negative infinity, that means that we are definitely a Setosa, because that means the log of this odd is very negative, which means it's very close to 0. Well, which means this ratio is very close to 0, meaning it's most probably Setosa. If this linear combination is very large, that means the log odds are very large, which means that the probability of versicolor is much larger than the probability of Setosa. Okay? And so the final interpretation that you get from this model is that the longer the petal length, the less likely it is to be Setosa, and the more likely it is to be versicolor or virginica. That is because the coefficient for petal length is positive for both versicolor and virginica in this output here. All right. That's all the time that I have for today. If you have any questions, then please let me know. And don't forget to prepare for the quiz that is on Wednesday, next class. All right. I hope everyone has a good day. I'll see you on Wednesday.